Hi everyone, my name is Anjali Sharma and today I am going to introduce you to the Sharma Research Laboratory at Washington State University. The Sharma Lab is a translational nanomedicines research laboratory where my group is working at the intersection of chemistry, engineering, nanotechnology and biology to develop clinically translatable nanomaterials to address unmet medical needs. If you look at the literature, a variety of nanoparticle-based therapies are currently being explored for drug delivery applications, but only a few nanoparticles can actually make their way to the stage of clinical trials. The biggest hurdle in the clinical translation of nanoparticles-based drug delivery systems or nanotherapies basically start with their synthesis process itself. Oftentimes, the design of nanoparticle formulation is so complex that it becomes extremely difficult to reproducibly scale them up. That causes batch-to-batch inconsistencies in terms of their pharmacological and biological properties. Here in the Sharma Lab, we are making use of very simple design and highly efficient chemistries to develop clinically relevant cell-targeted nanoparticles. We are using these novel cell-targeted nanoparticles for intracellular delivery of drug molecules to their targeted locations. Many times the small molecule drugs, even though they are very potent, have several drawbacks in terms of their bioavailability, dose-related cytotoxicity, and early clearance or the pharmacological profile. By attaching these drug molecules on the surface of nanoparticles, we are making sure to deliver these drugs to their targeting locations, thus increasing their efficiency and decreasing their side products, making them more clinically favorable.
Hello everyone, my name is Anubhav Dhul and I am a first year grad student in Dr. Sharma's lab. Here in our lab, we develop novel nanomaterials for unmet medical purposes. We mainly use click chemistry for synthesis of these nanomaterials. Here in this reaction, as you can see, we are stitching a nanomaterial with acetylene group as a terminating group and with a drug conjugate with azide as its terminating group. We use mainly copper 1 as our ion for this, as a catalyst for this reaction. So here in this reaction, as you can see, there is copper sulfate solution and I'm going to be adding sodium ascorbate solution to it for the production of copper 1, and as you can see the color is changing little by little, and this shows that the copper 2 is changing to copper 1 ions, and for our click chemistry approach this is perfect.
Good morning everyone. My name is Vikrant Vijjan and I am first year grad student working in Professor Sharma's lab. In this lab we perform different kind of reactions, and after the completion of reaction we purify the compound with different type of techniques, and from that there is one major technique which we use. It is column chromatography. Recently we have performed glycosylation reaction and now we are purifying our product with the help of column chromatography. So for this purpose we have to adsorb our material on silica. After that we pass that silica from this column. For this purpose we make different kind of proportions of solvent related to our product's polarity. So here we have put our silica. Now we are pouring our solvent from this side, and just because of their polarity, different materials came at different speeds. So now we are collecting our solvent. After that, when our desired compound will come, we distill with the help of rotoevaporator. It is the main function of column chromatography.
After the reaction has been completed, we use this combi flash to separate the products and purify the products. So we use this silica gel column to separate the products based on difference in polarities. We use solvent system, various kinds of solvent system like ethyl acetate, hexanes, DCM methanol. One of them is polar, one of them is non-polar. So based on basically difference in polarities, we separate our compounds from the reaction mixture in these test tubes. We inject them and the solvent system goes in, and the compounds, the various products in our reaction mixture come into these test tubes. Here is also a mass spec associated with this, and we can it reads the mass of various compounds and gives us peaks of compounds and their adducts. We can also directly inject samples into the mass spec, so it will give us peaks of the compounds here for different masses. This Combi Flash is also detects UV active compounds, so it is very helpful in separating UV active compounds.
My name is Sylvia and I'm an undergraduate researcher for the Sharma Lab. And here in the biospace, we do in vitro work. When dendrimers are synthesized in the synthesis lab, we pretty much test it on various cancer cells.
Hello everyone, I am Dr. Shivendra Yadav. I am working as a postdoctoral research associate in Professor Sharma's lab. My research interest lies in synthesis of complex sugar molecules and synthesis of novel glycodendrimers, its material and biophysical studies. We use microwave reactor for the reaction of novel nanoparticles. And this, we use microwave radiation to heat the reaction mixture. The main advantage of using microwave reactor over a traditional oil bath heating is in microwave reactor we can monitor the specific the exact temperature and the heating is uniform throughout the reaction mixture, unlike in the case of normal oil bath heating. Apart from that, by using suitable organic solvent, we can increase the reaction yield and decrease the reaction time as well.
So this is our HPLC high pressure liquid chromatography. We use it for the separation and purification of the analytes. This is where you would load the sample, and this is where it will get injected, and here is our detector. We can also convert the HPLC to GPC by just changing our detector to RI, the refractive index. We also sometimes can collect the fraction of the solutes. This is our fraction collector where we can collect the fractions and then test it as well. We basically work with nanoparticles in this lab, so what we use this HPLC is to determine the purity of the nanoparticles in this lab. We also use our HPLC for drug release studies. We conduct in vitro studies of the nanoparticles drug conjugates that is tested under various pH conditions with different buffers. That the buffers kind of mimic the plasma and the intracellular conditions, and from there we draw our calibration curve, and using that calibration curve we evaluate how much drug has been released at various time points.